Now let's have a look at the example where we want to solve the following width equation by using finite difference method. We are given width equation defined from x equal to 0 to 1, and then we also have a boundary condition at the left end, which is x equal to 0, and at the right end x equal to 1, and our boundary condition both are 0. And the initial condition, the first one is so meaning that our fx here is 1 over x sine pi x, and our gx equal to 0. And we need to use our h here, meaning that our h is 0.2, and our t, meaning that our time differencing, or k, equal to 0.1. Okay, and we want to solve this width equation by using finite difference method that we discussed before. So what we do here, the first step is, or step 1, we must draw our diagram. And if we draw our diagram, what we will have is, it is a y-axis, and this is our x-axis. And our x start from 0, so here meaning that x not equal to 0, and then we have with a grid spacing h 0.2, meaning that our x1 equal to 0.2, and then we have x2 equal to 0.4, and then we have x3 0.6, and we have x4 0.8, and the last we have x5 equal to 1. Okay, and our domain is defined from x equal to 1, which is, let's say I put black color to show our boundary, meaning that at this black one, all our value for u is 0, because it is given by boundary condition. And then with the time differencing is 0.1, and we also need to use from 0 to 0.1, so that we only need to determine the value of u at one level only. So let's say this is our next level, the dotted line. So this is j equal to 1. Here is j equal to 0, and here I equal to 0, here I equal to 1. x2 stand for I equal to 2, I equal to 3, I equal to 4, and I equal to 5. So that we at all the grid point, we have the value of u. So we have 1 here at the boundary, u here. So all grid point at the down here, we know from boundary condition, from the initial condition, and at the boundary we know what is the value, and then the value that we need to find, let's put blue now. Put blue, which is the displacement of u that we need to determine. So this blue is u1, 1, meaning that I equal to 1, j equal to 1. And then we have the next is u21, u31, u41, and u51 we know because it is at the boundary, so meaning that u51 equal to 0, and u50 also equal to 0 because it is at the boundary, while at the left boundary we have u00 equal to 0 and u01 also equal to 0. So we know, and from our initial condition we know that we are given initial condition. The first one is ux0 is equal to 1/8 sine pi x. So the first initial condition that we need to determine is when at this one, when I equal to 1 or x1 equal to 0.2, t0. So that here is u10 is equal to, where we can find it from. So meaning that u10 is equal to x1 t0 is equal to x1 is equal to 0.2 and t0 equal to 0. You just substitute our x now is equal to 0.2, 1/8 sine pi multiplied by 0.2. And if you calculate, what you will get is 0.0735. So at this point u10, our value is, that grid point is 0.0735. And then at this point ui is equal to 2, u20, and then it is equal to u20 is equal to u x2 t0 is equal to, our x2 is 0.4, u 0.40, 1/8 sine pi 0.4, and what you will get is 0.1181. For the u30 is equal to ux3 t0 is equal to u 0.60, 1/8 sine pi multiplied by 0.6, and then you will get 0.1181 also, same with the u20. And the last node that you need to determine is u40, where u40 you need to substitute x4, where our x4 is 0.8. It is 1/8 sine pi 0.8, and then here you will get 0.0735, and the next is 0 at the boundary. So here 0.0735, while u30 is equal to 0.1189, and same for the u20. So this is your diagram looks like, and you need to determine u11, u21, u31, u41, or at the blue grid points. And then we also have the second initial condition. The second initial condition is given by ut x0 equal to 0. And if we discretize, or if we approximate with centered difference, what you will get is ui j plus 1 minus ui j minus 1 divided by 2k equal to 0. And because we know that at t0, our j equal to 0, j equal to 0, or in bracket I can write t0. Therefore, our initial condition is u I1 minus ui negative 1 divided by 2 multiplied by 0.1, our k equal to 0. And you multiply, what you will get is ui1 equal to ui negative 1. And this is our initial condition. So that, if you remember our computational molecule, if you want to find the value at first u11 here, you must have three value. You must know three value. The first one is u00, and then u10, and also u20. And the next one that we don't know is that I circle green here, where if you draw the previous time level, the first green here is u 1 negative 1, and u1 negative 1, actually it is from this one when I equal to 1. So that we need to write also for I equal to 0 and 1, 2, 3, 4, and 5. Okay, so therefore we will get u0 1 is equal to u0 negative 1, in case we want to use it later. And then we have u 1 1 is equal to u1 negative 1. The next I is 2. u21 is equal to u2 negative 1. u31 is equal to u3 negative 1. And then the next is I equal to u4 1 is equal to u4 negative 1. And u5 1 is equal to u sub 5 negative 1. So you can see the use of this initial condition, as I told you, is this one that I put in the green. So that if you need what is the value of u1 negative 1, you can substitute also with u11. Okay, so that is the use for the initial condition. So the next step is, of course, you just reiterate to find the displacement distribution. Find what we need to find is u11, the blue one. If you look at the diagram, u11, and then u21, u31, and u41. Not a blue diagram, but blue grid points. So to find u11, Or maybe the next step, we should discretize first, because it is easy. Discretize our wave equation. And what we do here is our wave equation given by partial square u partial t square is equal to partial square u partial x square. So meaning that at this example, our c square is 1. And if we use the centered difference, what we will get is ui j plus 1 minus 2 uij plus ui j minus 1 divided by k square is equal to ui plus 1 j minus 2 uij plus ui minus 1 j divided by h square. And if you multiply both sides by k square, what you will get and simplify like we did previously, you will get ui j plus 1 is equal to k square divided by h square ui plus 1 j plus 2 minus 2 k square over h square uij plus k square divided by h square ui minus 1j minus uij minus 1. And if you substitute, k square over h square is equal to r, you will get r ui plus 1j plus 2 minus 2r uij plus r ui minus 1j minus uij minus 1, where our r is k square divided by h square. And this is our finite difference equation for wave equation, where we need to use the value of I 1, 2, 3 and 4, because we need to find u1 1 and so on, and of course our j is 0. And with value of k and h equal to k is equal to 0.1 and h is equal to 0.2, what you will get for our finite difference equation is ui j plus 1 is equal to 0.25 our r ui plus 1j plus 1.5 if you calculate uij plus 0.25 ui minus 1j minus ui j minus 1. Okay, and we need to find the value for I equal to 1, 2, 3 and 4 and j is equal to 0, sorry, because we only need to find only one time level. If you ask for example 2 or 3 time level, and then of course your j 0, 1 and 2 depend on the question. And then the next, of course, we need to reiterate when I equal to 1, j of course it is 0, you will get your u11, your first grid point that is blue, that if you see in the previously in your diagram, so that you will get u11 equal to 0.25 u20 plus 1.5 U10 plus 0.25 U00 minus U1 negative 1. And again, if you see in your diagram or what you already calculate before, this U20 is located at the initial condition or at the t equal to 0, so that you know the value of U20. It is 0.1189. U10, you know it is 0.0735. U00 at the boundary, it is 0. And U1 negative 1, you know that from the initial condition also, it is U11. And you can bring U11 here to the left because it is same like to the left one that we need to find, so that you will get 2 U11 is equal to 0.25 multiplied by 0.1189 plus 1.5 multiplied by 0.0735 plus 0, and you will get your U11 is equal to 0.0699 or 0.07. Okay, this is your solution. And then the next is you need to iterate for I equal to 2, j equal to 0. And then if you do, you will get U21. U21 is equal to 0.25. U30 plus 1.5. U20 plus 0.25. U10 minus U2 negative 1. And again, if you look at your diagram or what you already calculate in the initial condition, U30 is equal to 0.1189. U20 also is equal to 0.1189. U10 is equal to 0.0735. And this U21 is equal to U2 negative 1, sorry. And you can bring this U21, bring to the left. And then you will get 2. U21 is equal to 0.25 multiplied by 0.1189 plus 1.5, 0.1189 plus 0.25 multiplied by 0.0735. And then the thing that you need to find is U21 is equal to 0.1132. This is your value of U at grade 2-1. And then the next is you iterate I equal to 3, j equal to 0. And if you iterate, you put I equal to 3, j equal to 0 in the finite difference equation. What you will get is U31 also is equal to 0.1132. And the last one is I equal to 4, j equal to 0. What you will get is U41 equal to 0.07. So now, if you see our value U11, U21, U31 in U41, if you draw a little bit, so now let's draw with black one. So we know that at the boundary, so this is, let's say this is our domain, right? So this is x equal to 0, and this is x equal to 1, I guess, our problem. At the boundary, we have this 0. Of course, it is 0. Let's say now we are talking at this current time level. And then U11 is 0.07. So let's say 0.07 is somewhere here. And then the next one is 0.1132, this one. And the next grid point, again, it is 0.1132, this one also. And the same one, and then the next one is 0.07. Okay, and then the next one, of course, it must be at the boundary, it is 0. Okay, I'm sorry. Maybe we should put our right hand boundary at this one, x equal to 1, so that if you continue, or if you follow this one, your solution, you will get a kind of wave. Okay, this is a kind of wave with half period. So this is talked about wave equation. Of course, you have a displacement up and then down, and we have solved this one by using finite difference method. And if you draw properly, you will get like this. It's like a rectangle. It's like a rectangle. It's like a triangle, sorry. And then this is the problem for the finite difference method. If you take a very big grid spacing, and then we cannot see the what we want, or meaning that our solution got error. But if you use very small grid spacing, and then you can see the wave. So this is for the finite difference method, and I guess for all the numerical method, we need to use a very small grid spacing to get a more accurate answer or more accurate solution. Okay, so that is what you need to know about wave equation, how you discretize the wave equation, and also how you discretize the initial condition. Oh, that's all for now. Thank you very much.